So I thought I'd do a video on the IA2 projectile motion assignment that you have coming up. We've read through the task sheet, but essentially you're going to modify by either refinement, extension, or redirection of an experiment in order to address your own hypothesis or question. You may use a practical performed in class. We're going to use the mandatory prac that we've done. And that mandatory prac that we've done, if you scroll down, is essentially here, where we rolled the ball bearing through a circular tube and projected it at a set angle from the end of the pipe. The initial velocity then is varied by changing the kinetic energy, by changing the height of the pipe. We did this one in class. So I went and did up a prac for this, a prac write-up. The aim is to determine the projected range of a ball bearing rolled down a ramp. There's a list of the apparatus that we have here and a method. And if you remember, we got the end of the pipe, we held it up at different heights and dropped the ball bearing down through that, through the tube. And there's a procedure here, step-by-step procedure. And just to make it sort of clear, I guess, because you need to modify the prac, and modifying the prac can be difficult if you don't exactly know what the prac was. So if you just remember, let me just draw a diagram of the equipment that we had. So essentially, if you remember, we had like a piece of board, piece of timber. We had some screws on that timber that had the pipe then come out at a particular angle, and the ball ejected out of here. And if you remember, we had like a sand pit. So that was a table height there. And we had a sand pit, and we made the sand pit, or the level of the sand, essentially the same height as the bottom of the pipe here where the ball's ejected from. And the reason why is because when we drop the ball from here, that height there, that is its gravitational potential energy, and gravitational potential energy is mg delta h. This delta h is not, so this is sitting on the table. The delta h is not the distance from the floor to the table. The delta h is the distance that the ball actually drops. And in this case here, it's going to drop to this point, to the bottom of that tube. That there is actually the change in height. So we can get the gravitational potential energy here, and we can work out its difference in gravitational potential energy here by using this formula, mg change in height. And if you remember then, we actually went and changed the height of this tube. So we bent the tube at different heights, and we measured the difference in those in the height from here to here. And we had different change in heights, and that gave it different gravitational potential energies, so that we can work out at this end here the kinetic energy. And we'll go through that in a little bit more detail. But one of the things we need to make sure that we did was we kept this height here that we're dropping the ball bearing from consistent at each stage. That was a little bit difficult. We did it, but I don't know that it was overly accurate, and that's something that you might look at in terms of refinement later on. We need to make sure that that sand pit was exactly the same as this level here, because if we're using that change in height, this delta H here, if that sand is down here a little further, well, now the ball would be ejected from here and it would travel actually further down, and that'd be problematic in trying to figure out the actual the range when we do that later on. If you remember, we actually had three people standing watching, and each of those people had a stopwatch, and that stopwatch, on that stopwatch we measured 3 times at the same time for the time that it took for the ball to come out and land into the sand. And we then got the average of those 3 times, and we put that time then into a table, and we averaged those times again. We also then we put this in sand so that we had a bit of a divot where the ball landed, but if you look at it from the top, if this is a sand pit sort of looking from the top, then the ball would sort of hit, but it also then sort of spray a little bit as well. And so calculating that exact edge there was a little bit problematic as well. Maybe you could look at doing some other stuff like maybe plasticine or something like that, so that you get an exact dot, and maybe the ball would stick and it wouldn't go any further, maybe plasticine or Play-Doh or something like that, so you can get that exact distance, as opposed to, we probably had an error of plus or minus 1 centimetre. I'd say to be something like that, and maybe even more. The stopwatches also, we had 0.2 plus or minus 0.2 seconds, and if you look at some of the times, the average time that it was measured for, we're talking about 0 0.51 seconds was the average time of flight. And if that's the average time of flight, we've got that plus or minus, 0.2 seconds, then that there's almost, what's that going to be, about 2/5, so 40% error or potential error, inaccuracy in our measurement, which is quite significant. So maybe you could look at tightening up these time intervals as well. Maybe you could look at using a video camera instead of just doing it with a stopwatch. I'm sure that would make it a lot more accurate. And if you do it with a video camera where it was only going at, even if it was doing something like 27 frames per second, then even that is each frame is 1/27th of a second, which is significantly smaller than the uncertainty of 0.2 seconds that we have with a stopwatch. So that would be a lot better. You could even increase that by, if you did a high frame, sort of high-speed camera, you might be looking at something like 1/300th of a second, where it does 300 frames per second. You can get, as close as possible to the exact time that ball hits the plasticine or the sand or whatever equipment that you're using. Once we got all that data, we put it into a table, and I've put a summary table in here, a summary of the range and the TF, big T, little subscript F, that is for the total flight, total time of flight, and the R equals range, the range in the flight, the range I should say of flight, so where the ball actually landed, the ball bearing landed in the sand. You measured the distance from the end of the pipe to that sand, and that gave us a range. And this is a summary sort of table, I guess, of all of that data. And what we need to do then, I guess, is go now and look at the more detailed results table, and we'll look at trying to calculate some of the results in that. But before I do that, I'll do that in a separate video, but before I do that, let's just have a quick look here at the setup as well. Because one of the other things I put in the procedure was using an online protractor to calculate the average, the angle. And if you look on that piece of pipe, then down here, there's actually a black line that I've drawn on that piece of pipe, and I'm going to sort of project that out here somewhere, and try and work out the angle, I guess. And that wasn't a very straight line. I think I measured it at about 27 degrees or something like that off this photo, but obviously there's quite a bit of uncertainty in that as well. You might be, I don't know, plus or minus, 4 degrees Celsius, 4 degrees might be fairly conservative in terms of the amount of error or uncertainty that could be using this online protractor. The next video I'll do will be on the results section. So we've gone through the procedure, we've got down the results, and I'll show you the results table and how I want to calculate. Then I'll put the formulas in, and I'll show you how to calculate each of these values.